Welcome to today's paper reading. Today's paper is titled, AlphaMath Almost Zero, Process Supervision Without Process. This paper was published in the 38th Conference on Neural Information Processing Systems, NeurIPS 2024, by Guoxin Chen and colleagues from Tony Lab. The abstract highlights the challenges faced by large language models, LLMs, in complex and symbolic multi-step reasoning, particularly in mathematical reasoning. To address these challenges, the authors introduce AlphaMath, a novel framework that utilizes Monte Carlo Tree Search, MCTS, without the need for process annotations from humans or GPT-4. This framework integrates a value model with the LLM to enhance mathematical reasoning capabilities. The experimental results show that AlphaMath achieves comparable or superior performance to state-of-the-art methods without relying on GPT-4 or human-annotated process supervision. The current approaches to improving mathematical reasoning in large language models, LLMs, involve fine-tuning with high-quality, process-supervised data annotated by domain experts or GPT-4. However, these methods underutilize the vast knowledge already present in LLMs. Advanced techniques like program of thought, POT, and program-aided language, PAL, have been developed to integrate in-context learning with external tools for precise computation. In this research, we propose a novel approach that integrates LLMs with a Monte Carlo Tree Search, MCTS, framework and introduces a step-level beam search strategy to autonomously generate high-quality mathematical reasoning solutions without professional human annotations. Table 1 compares the annotation costs between human and GPT-4 sources. It highlights the methods used by 21, 46, and 14, 25, 38, and introduces the annotation approach of AlphaMath. This table is crucial for understanding the different strategies employed in obtaining high-quality process-supervised data, which is essential for enhancing the mathematical reasoning capabilities of large language models. In this preliminary section, the authors introduce a reinforcement learning framework for mathematical problem solving. They define the state ST as the partial solution at time t, and the action at as the subsequent reasoning step. The transition from one state to the next is deterministic and achieved through concatenation. The primary objective is to develop a step-level value model, VS, which evaluates the expected returns from the current partial solution. The reward structure assigns 0 to non-terminal steps and plus or minus 1 to correct or incorrect final answers. The value model is trained using a regression loss, LVS, based on Monte Carlo evaluation. The policy model, represented by a large language model, is optimized alongside the value model to guide the selection of more reasonable reasoning steps. Figure 1 illustrates our approach to mathematical reasoning through an iterative process divided into 3 distinct stages. The first stage involves collecting a mathematical dataset that includes questions paired with their final answers. In the second stage, Monte Carlo Tree Search, MCTS, is employed on both the policy and value models to generate both correct and incorrect solution paths, along with their associated state values. The third stage focuses on optimizing the policy and value models using the data generated from the MCTS process. This iterative framework aims to enhance the model's ability to autonomously generate high-quality mathematical reasoning solutions without the need for professional human annotations. In this section, we discuss the evaluation of the Monte Carlo Tree Search, MCTS, algorithm and the iterative training process. The MCTS evaluation involves iterative training with a value model VK and a policy model pi theta k for inference. These models are used to construct an inference algorithm that customizes the 4 key operations of MCTS specifically for mathematical problem solving. The key operations include selection using a variant of the PUCT algorithm, expansion through sampling generation, and evaluation using a weighted sum for leaf nodes. The iterative training process begins with an initial LLM policy model pi theta 1 and employs a multitask loss function to update both the policy and value models. This iterative process enhances the models through repeated MCTS simulations. Figure 2 provides an overview of the 4 key operations in the Monte Carlo Tree Search, MCTS, algorithm. The selection phase uses a variant of the PUCT algorithm to choose nodes. Expansion involves sampling generation with higher temperature to ensure diversity. The evaluation phase combines the value model's estimation with empirical rewards using a weighted sum. The backup phase updates state action values and visiting counts. The training data for this study consists of 15,000 question and answer pairs extracted from GSM-8K and math datasets, without including the human annotated solution analysis. The MCTS framework is utilized to generate detailed solution processes with a Python code interpreter. The initial prompt follows the React format, incorporating 2 demonstrations randomly selected from a pool of 20 examples. For subsequent rounds, a straightforward prompt in SFT XML format is used without any demonstration. The test data includes GSM-8K, Math, Gaokao 2023, and OCW courses datasets, which are evaluated using the Math Evaluation Toolkit. These out-of-distribution datasets are more challenging than Math. Table 2 presents the main results of various models, highlighting the performance of open-source models in bold. The table includes performance metrics for models where outputs have been released, using the Evaluation Toolkit 47. It also notes the impact of seed data, which refers to high-quality annotated question-solution pairs, typically created by humans or GPT-4. The default settings for beam size and step-level beam search, SBS, and the number of simulations in Monte Carlo Tree Search, MCTS, are also specified unless otherwise noted. Table 3 provides an analysis of computational efficiency on the math dataset, focusing on various inference strategies such as greedy, Mach at 5, and different configurations of SBS and MCTS. The table highlights the accuracy, ACC, average time taken, average, time, S, average number of steps, average, steps, and the number of solutions obtained, #SOL. Key observations include the increase in accuracy with larger beam sizes in SBS, the higher computational demand of MCTS, and the unique mechanics of candidate selection and retention in Mach at 5 compared to SBS. Table 4 presents additional results on the performance enhancement of Llama 3 and Mario models. Notably, AlphaMath significantly boosts Llama 3's mathematical reasoning capabilities, achieving an average improvement of plus 20 points. Additionally, AlphaMath enhances Mario's performance, making it competitive with and sometimes surpassing GPT-4. The table also highlights that DeepSeek MathBase 7b, a domain-specific pre-trained model, outperforms the general-purpose Llama 3 model, emphasizing the importance of specialized knowledge in mathematical reasoning tasks. Figure 3 illustrates the problem-solving rate at different difficulty levels on the math training set. It highlights that Monte Carlo Tree Search, MCTS, achieves greater success in solving more challenging problems as the rounds progress. This indicates an incremental improvement in the model's ability to solve complex problems over time, reflecting the enhanced quality of self-generated training data with each round. Figure 5 presents the fitted distribution of Q-values in Monte Carlo Tree Search, MCTS, across different datasets. The left panel shows the Q-values distribution for the third round of MCTS on the training set, highlighting a skewed distribution towards 1 for correct solutions and a less skewed distribution for incorrect solutions. The right panel displays the Q-values distribution on the test set, where correct solutions maintain a similar shape to the training set, but incorrect solutions show a bimodal pattern, indicating instances where the value model incorrectly labels incorrect solutions as correct. Figure 6 illustrates the impact of temperature on the performance of step-level beam search, SBS. Firstly, SBS consistently outperforms the greedy strategy across all temperature settings, thanks to the value model aiding the policy model in identifying effective reasoning paths. Secondly, at lower temperatures, SBS performance is constrained due to the lack of diversity in generated solutions. As temperatures increase, the value model can discern optimal paths within a more diverse set of solutions, thereby enhancing reasoning performance. Finally, with larger beam widths, the model explores more solutions, so the performance of B1 equals 3 always surpasses that of B1 equals 1. In the field of mathematical reasoning, recent works have shown significant progress, particularly through the use of process-supervised data. However, these efforts often rely on high-quality solutions provided by domain experts or advanced models like GPT-4, which limits scalability and increases costs. On the other hand, value and reward models have demonstrated the ability to enhance reasoning performance, but they require substantial annotated data and can introduce significant delays in inference. In contrast, our approach leverages large language models to achieve self-evolution and integrates state values from Monte Carlo Tree Search to align with solutions, thereby reducing annotation costs and enhancing the efficiency of reasoning processes. In this study, the authors introduce AlphaMath, an innovative training paradigm that employs iterative methods and Monte Carlo Tree Search to maximize the potential of a pre-trained large language model. This approach allows the model to autonomously improve its mathematical reasoning skills. Additionally, the use of step-level beam search, where the value model aids the policy model in choosing a more logical solution path, enhances reasoning capabilities significantly with minimal additional cost. The experimental results show that AlphaMath performs competitively or even surpasses state-of-the-art methods on both in-domain and out-of-domain datasets, without the need for GPT-4 or human-annotated process supervision. Thank you for watching.